Wait a minute. So it is sum of the bloody. Okay. So today we are discussing about the D block elements. In this D block elements, so which are called as D block elements and
Ma'am, it's too blur.
it is too blurry. Okay, I will send the another one. Wait a minute. Can you write this? Now it is clear?
Yes, ma'am.
Okay. So here today we are discussing about the D block elements. In these D block elements, we are discussing about the D block elements are classified into how many series and what are the oxidation states of D block elements and what are the magnetic properties of D block elements, what are the catalytic properties and the complex properties of the D block elements. Okay. So look at this, today's class, look at this introduction. The elements lying between the S block and P block elements of the long form of the periodic table are collectively known as transition elements. So these elements, either in their atomic state or in any of their common oxidation state, partially filled N-1D D1 and NS2 or N-1D 1 to 10 NS2. It is for the reason they are called named as P block elements. Okay, look at this. Suppose this is the rough diagram of periodic table. In this rough diagram, so these elements, so these box elements are called as D block elements, and these are the S block elements, these are the P block elements, and these are the F block. The middle one is D. Okay. The D block elements are situated in between the S and P orbitals. Okay, and why these are called as D block elements? Because the differentiating electron is entering into the d orbital. So that's why these elements are called as D block elements. And the D block elements electronic configuration is N-1D 1 to 10 NS2. So this is the general electronic configuration of D block elements. Okay. Then these D block elements are classified into various groups or series. Okay, 3D series, 4D series elements, 5D series elements, and 6D series elements. Okay. So the D block elements are classified into the 4 series, 3D series, 4D series, 5D series, and the 6D series. Okay. Look at this. In this structure, look at the bottom. So in first series, the 21 to 30 scandium to zinc atomic number elements are called as 3D series. In second series, yttrium to cadmium 39 to 48 atomic number. Okay, and each series it has 10 electrons. And the 3D series, lanthanum to hafnium. In the fourth series, 89 to 104 element and 105 elements are present. So these are classified into 4 series. Then the next topic is some physical properties of the or characteristics of the d block element. In transition elements, the differentiating electrons are entered into n-1d orbitals in presence of the ns orbital. These elements are therefore expected to have many physical and chemical properties in common. The elements of the group having n-1d, 10 and ns2 electronic configuration shows some differences from the remaining elements. So all the transition elements are metals and the number of electrons in the outermost shell is small, being equal to 1 or 2. They are hard, malleable and ductile and having good character of heat and electricity. So they possess all the 3 types of structures, namely face-centered cubic and hexagonal close packing and body-centered cubic. Okay, once I repeat. So here in the d block elements, the normal electronic configuration is n-1d, 10 and ns2. Generally, the d block elements, the transition elements are having the metallic character. Due to the metallic nature, they are acting as having the malleable nature and ductile nature. That means they are converted into the voids as well as they having the hotness and they can make as the plate like the apparatus. Okay. And these are acting as the good conductors because the electricity is passed easily, because these are having the d orbitals are having empty orbitals. So due to the vacant orbital, the electron transfer is very easily occurs. So that's why these are having the electricity nature also. Okay. Then the transition elements having partially filled n-1d orbitals has very high melting and boiling points as compared to those of S and P block elements. Okay. So these transition elements are having the high melting point values. Okay. Melting point and boiling point values. Because, so in n-1d, some are having the filled orbital, some are having the partially filled electrons are present when comparing with the S and P block elements. Okay. Here the zinc, cadmium, mercury having completely filled orbitals possess relatively low melting and boiling point values. Okay. Here the zinc, cadmium, mercury in the d orbital, they are having the 10 electrons. So that's why they are due to the fulfilled electronic configuration. Due to the fulfilled electronic configuration, they are having the low melting and boiling point values. Okay. So here, so these are the some of the transition elements their covalent radii. Suppose we can take the calcium. So this is not the D block element. Its covalent radii is 1.74, and the scandium to zinc, these are the transition elements and D block elements. The scandium, it is having 1.4 for covalent radii, titanium is 1.32, vanadium 1.22. So just like the nickel is having 1.15 angstroms and copper is having 1.17 angstroms. Okay. So just like ytterbium is having the 1.91 angstroms covalent radii and cadmium is having the 1.4. Okay, look at this. When the atomic number is increases, the covalent radii should be decreases in the D block elements. So it can be seen from the table that these values first decrease from the scandium to vanadium. Okay, but latter remains closer to one another from chromium to copper. Look at this here, scandium 1.44, titanium 1.32 angstroms, vanadium is 1.2. When these values 10, 10, 10, 10 points should be decreases. When comparing with this, the chromium is 1.17, manganese is having 1.17. Both are having the same covalent radii because in the chromium, due to formation of half-filled electronic configuration, so it is having 3d5 half-filled configuration, and the manganese, it is having the 3d5 and 4s2 electronic configuration. And iron also having the similar configuration. Cobalt is 1.16, nickel is 1.15 angstroms is present. Okay. So here, this is due to the fact an increase in the effective nuclear charge tends to attract the electron cloud, decreasing the radius from the scandium to vanadium. Okay, scandium nunchi vanadium variki decrease ayindi. Endukante due to the attract of the electron cloud. 4s electrons from the nuclear attraction resulting not much
Excuse me, ma'am, your voice is breaking.
Ayyo nama, వినిపించట్లేదా? It is not clear. Hello.
Hello. Excuse me, ma'am, your voice is breaking.
Acha. Okay. Hello. Now, am I audible clearly? Now, am I audible clearly?
Yes, ma'am.
Huh?
Yes, ma'am.
Okay. So, the covalent radius from chromium to copper, in the first group, the atomic radius show expected increase in size, scandium to ytterbium to lanthanum. But in the subsequent groups, an increase in the radius is 0.1 to 0.2 angstroms between the first and second transition series, and the remain constant in the third transition series. So this is known as the lanthanide contraction. Okay. So the effect of the lanthanide contraction being to die out toward the right of the D block elements, and hence the radii should be increases. The first ionization energies of transition elements lies between the values of those of the S and P block elements. The addition of the differentiating electron to N-1d level in the transition elements provides a screening effect, shielding the outer NS electrons from the nuclear attraction. So thus the effect of the effective nuclear charge and shielding due to the energies. So increase rather slowly along a period. The forced ionization energies of zinc is considerably high because the completely filled d and s orbital. Okay. Then look at this. Wait a minute. So this is the forced ionization energies of the transition elements. The scandium, it is having 631 kilojoules per mole. Titanium is 656. Vanadium 630. Just like copper is 745 and zinc is 906. So when the atomic number is increases, then the ionization energy values also increases. Okay. The transition elements are characterized by the following: by the formation of compounds containing the metals in different variable oxidation states, paramagnetic compounds, colored compounds, complex compounds, and alloys. The compounds in different oxidation states, catalytic activity. So these are the some of the functions of the D block elements. Here first we are discussing about the oxidation states. May I audible clearly?
Yes, ma'am.
Okay, the oxidation states. The chemistry of transition elements is characterized the phenomena of variable oxidation state. This is due to the presence of valency electrons into different sets of orbitals of almost similar energy. The 5 degenerate N-1d orbitals and 1 ns atomic Hello? Hello? Hello, may I audible? Hello?
Yes, ma'am, you're
Hello?
audible.
Yes, ma'am. Yes, ma'am.
Thank you, thank you. So here we are discussing about the oxidation states. Okay. So generally this is the formula of D block elements. N-1d, 1 to 10, NS2. So in the formation of oxidation state, so the D block elements as well as the S block elements, both are involved in the oxidation state. Let us see one example, that is, suppose you can take the scandium. Okay, the scandium atomic number is 21 and its electronic configuration is argon 3d1, argon 3d1, 4s2. Okay, so here if the scandium, suppose it is in +1 oxidation state, it loses 1 electron from the d orbital. If the scandium In +3 oxidation state, it loses the 3 electrons from the outermost orbitals. Then it is converted to scandium +3. So due to this reason, in the electronic configuration, in the oxidation state, N-1 d orbital and the Ns orbital both are involved in the oxidation state. And these are having the variable oxidation state because in the d orbital, they having 5 d orbitals are present like this. Okay, so these are the 5 d orbitals and the s orbital. So this is about Nd. N is nothing but it is a 3D series element or 4D series element or 5D or 6D. Okay, so here the d orbital, it is having the vacant orbital and sometimes s orbitals also having the vacant. So due to the vacant orbitals present in the d orbitals and they are having the small size, due to this reason they are having the variable oxidation states. Look at this. Here, the manganese, it is having the +3 oxidation state, +4 oxidation state, +5 oxidation state, and +6 oxidation state. How it is having these various types of oxidation state? Look at this. So this is the manganese. Manganese atomic number is 25. Its electronic configuration is argon 3d5 4s2. So in outermost orbital, it is having the totally 7 electrons. That is, the d orbital is having the 5 electrons and s orbital is having the 2 electrons. 3d5 4s2. Okay. So if it lose one electron, then +1, 2. Suppose it lose, it is having the +3 oxidation state. Mn +3 oxidation state. In this, it lose 2 electrons from the s orbital, 1 electron from the d orbital. Then it is converted to 3d4 electronic configuration. If manganese is having +4 oxidation state, it lose 2 electrons from the s orbital and 2 electrons from the d orbital. Then it is having the 3D 3 electronic configuration. If it is having +5 electronic configuration, then it lose 2 electrons from the s orbital and 3 electrons from the d orbital. Then it is having 3d2 4s 0 electronic configuration. Okay. If it is having the Mn +5 electronic configuration. In Mn +5, okay, next is about the Mn +6. It lose 5 electrons, 4 electrons from the d orbitals and 2 electrons from the s orbital. Then it is having the 3d2. Okay. So here, just like it is having the variable oxidation state by loss of the electron from the d orbital as well as the s orbital. Okay, somebody requesting for organic topic. So today I have to complete this topic. Okay, then tomorrow onwards, okay, we are studying about the organic. Understood?
Okay, ma'am.
Somebody kept a message in this message box. That is, what is that? Wait. Recording. Wait. Somebody asking about organic water, ma'am. I have a request that please teach the organic part because we can read inorganic part by ourselves also. Okay. So tomorrow onwards we start the organic topic. Then look at this table. In this table, the various oxidation states are present. The scandium, it is having the +3 oxidation state. Titanium, it is having +2, +3, +4 oxidation states. And vanadium is having +2, +3, +4, and +5. Just like manganese is having the +7 oxidation state. This is the highest oxidation state because in manganese 3d5 4s2 electronic configuration is there. So due to that reason, it loses the 7 electrons and having the +7 oxidation state. Can anybody say the zinc is having the +2 oxidation state only maximum? What is the reason? Hello. So look at this. The zinc atomic number is 30. Its electronic configuration is argon 3d10 4s2. It loses 2 electrons from the s orbital. Then it is converted to Zn+2. Its configuration is argon 3d10 4s0. Okay. So this is the zinc is having the +2 oxidation state, then it is stable. Okay. So in +3 it is not stable. So that's why the +2 is the stable oxidation state. Because in +2 oxidation state, the d orbital is having the full electronic configuration and the s orbital is having the empty orbital configuration. Then look at for this copper. So here the copper atomic number is 29. Its electronic configuration is argon 3d10 4s1. Actually, we can write like 3d9 4s2. But it is not a stable electronic configuration due to formation of stability. So the copper is involved in the 3d10 4s1 electronic configuration. Okay. (3d10 4s1 electronic configuration) because 3d10 is the full field electronic configuration, 4s1 is the half field electronic configuration. When an element which possesses the full field configuration or half field electronic configuration, then only it gets stability. So due to formation of stability, it is having this type of configuration. So the copper itself, it is involved in the, actually when it is involved in the +1, copper +1 electronic configuration, it loses 1 electron from the s orbital. and it get the stability electronic configuration. So here the copper plus 1, in the copper plus 1 it is more stable. Sometimes it is having the plus 2 as well as plus 3 oxidation states. Then look at this. In the 4D series, the zirconium to cadmium, yttrium to cadmium. So in this also, the ruthenium is having the plus 8 oxidation state. In the 5D series, lanthanum to mercury, the osmium is having the plus 3 oxidation, plus 8 oxidation state. Okay. So here the D block elements are having the variable oxidation state. The lowest oxidation state for the 3D series is plus 1. It is for the copper. And the highest oxidation state for the 3D series element is plus 7. That is for the manganese. Okay. Then moves to 4D series. In the 4D series, the lowest oxidation state is plus 1. That is for the silver, Ag plus 1. And the highest oxidation state is ruthenium. It is having the plus 8 oxidation state. Then next is about the 5D series, that is lanthanum to mercury. So in this, the lowest oxidation state and the highest oxidation state is plus 8. So this plus 8 regarding for the osmium, plus 1 for the gold and the mercury. Okay. In the D block elements, the highest oxidation state is plus 8. It is for the ruthenium and osmium. And the lowest oxidation state is plus 1. It is belongs to the copper as well as mercury and copper, silver, mercury, gold. 1 minute. Wait a minute. Okay, so this is the oxidation state calibration part. Okay, so here look at this manganese. The manganese, it is having the variable oxidation state and it is reacted with the oxygen, manganese tetroxide, MnO2. Okay, so these are having the different oxidation state, and in this different oxidation state, they have different electron potential values. Look at this here, Mn plus 3. In this, the manganese is having plus 3 oxidation state. In MnO2, the manganese is having the plus 4 oxidation state. In MnO2, it is having the plus 6 oxidation state. In MnO4, it is having the plus 7 oxidation state. Then discussing about the magnetic properties. So here the transition metal atoms possess unpaired electrons. The atoms are ions, which unpaired electrons are paramagnetic in nature, whereas those containing pair electrons are diamagnetic. The paramagnetic movement of compounds and n unpaired electrons is given by the equation. Okay. So here, which are called as magnetic substances, the magnetic substances are classified into various types. So in this, mainly we are discussing about diamagnetic substances and paramagnetic substances. So which in the presence of external magnetic field, the substance which repelled by the external magnetic field, that is called as diamagnetic substance. Once I repeat, the substances which are repelled by the external magnetic field, those are called as diamagnetic substances. The substances which are attracted by the magnetic field, those are called as paramagnetic substances. In paramagnetic substances, unpaired electrons are present, or single electrons are present in the paramagnetic substance. Based upon the unpaired electrons, we can calculate the magnetic momentum of a substance. So here there is a equation. Look at that equation. The mu is equal to under root of n into n plus 2. So here the Bohr magnet, that means the magnetic momentum, it is calculated by, it is expressed in the terms of Bohr magnet, Bm. Bm is nothing but the Bohr magnet. And the d block elements which are having the paired electrons are vacant orbitals. Those are acting as the diamagnetic substances. Okay, once I repeat, the magnetic substances are generally classified here only two types. One is paramagnetic substances, second one is diamagnetic substances. The substances which are repelled by the external magnetic field, those are called as diamagnetic substances. So these diamagnetic substances are having the paired electrons or vacant orbitals. Look at this scandium. Already we know that the scandium atomic number is 21. Its electronic configuration is argon 3d1 4s2. So here in this, if the scandium is in +3 oxidation state, its electronic configuration is argon 3d0 4s0. So at this time, this scandium is acting as the diamagnetic substance. Just like we can take the copper. Copper atomic number is 29. Its electronic configuration is argon 3d10 4s1. So 3d10 is nothing but the d orbital containing 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4s1. Okay. So if this copper, it is in the +1 oxidation state, it loses 1 electron from the s orbital and it is having the fulfilled electronic configuration. So due to this reason, this copper +1 is acting as the diamagnetic substance. Next, look at for the paramagnetic. So which is called as paramagnetic substance. The substances which are attracted by the external magnetic field are called as paramagnetic substances. So the condition is that the paramagnetic substances compulsory having the unpaired electron. Look at this, the scandium also here example. The scandium atomic number is 21. Its electronic configuration is argon 3d1 4s2. If the scandium in +2 oxidation state, It loses 2 electrons from the s orbital. Then its configuration is argon 3d1 4s0. So here the scandium in +2 oxidation state, it is having in the d orbital, it is having only one unpaired electron. So that's why the scandium in +2, it is acting as the paramagnetic substance. Same scandium in +3, it doesn't having any single electron in the d and s orbital. So that's why in +3 oxidation state, it is acting as the diamagnetic substance. So there is a difference between the dia and the para. And the paramagnetic substances, magnetic momentum, it is calculated by an equation. Wait. So here the equation for calculation of magnetic momentum, that is equal, mu is equal under root of n into n plus 2. And the mu, the magnetic momentum, it is represented in terms of Bohr magnus values. Okay. So look at this. Here are the different magnetic momentum of the component, and the calculated magnetic momentum is different from the practical magnetic momentum. Okay, or it is called as determined magnetic momentum. Here the titanium +3 and vanadium +4, both are having a single electron in the valency shell, and these are having 1.73. So it is the calculated formula that is based upon that principle. The mu is equal to under root of n into n plus 2. But the experimental values are 1.7, in between the 1.7 to 1.8. Okay. Then titanium +2 and chromium +4. Those are having the 2 unpaired electron, and the magnetic momentum of calculated is 2.83, and the magnetic momentum of determined, that is experimental, is 2.8 to 3.1. Just like the copper in +2 oxidation state, it is having one electron in the unpaired electron, one is there, and its magnetic momentum is 1.73. And the experimental value is 1.9 to 2.1. Okay, so this is regarding for the magnetic momentum. And in this class, you have the color properties, complex compounds, as well as the, so these two topics are remaining in this. So tomorrow we are discussing about these two topics. Then next start about the organic chemistry. Okay, if you may have any doubts, let's clarify in the class. Okay. Thank you.
Ma'am, what is Bohr's magneton, ma'am?
I'm not here properly.
That Bm, ma'am, in the formula itself, ma'am.
BM, Bohr magnet.
Yes, ma'am, that
Formula?
only.
So is it, you wanted a formula?
No, ma'am, what is that Bm, ma'am, in the formula? That I want to know.
Capital B, small m. Capital B, capital M. That is called as Bohr magnet. already in this they are written. Wait,
Ma'am, you are not audible.
not audible. So here the BM it is nothing but a bore magnet. It is clear, it is visible. Hello.
Yes, ma'am, it's clear.
Okay. Any doubts regarding the topic?
Ma'am, in osmium, why it is not having +7 oxidation state, ma'am?
Uh,
In osmium, ma'am, why it is not having +7 oxidation state, ma'am?
which one?
Osmium, ma'am, osmium.
Based upon actually in the task name, the F block elements are just F block elements are moving to them now. So due to the lanthanide contraction, maybe it is not having the +7 oxidation configuration.
Okay, ma'am. Thank you, ma'am. चलो क्लास वाले घरों को जाओ पूरे